Welcome to part 5 of Maxvi's Verilog tutorial series. In this video, we will discuss about data types in Verilog. Alright everyone, here's what we'll be covering today in our Verilog tutorial. This session is divided into three main parts to help us understand some fundamental concepts. First, we'll delve into the value set. This section will cover the different values that variables can take in Verilog. Next, we'll move on to strengths. This might be a bit new for some of you, but it's important. We'll discuss how Verilog models the strength of signals. Finally, we'll explore net data type. Nets are essential in Verilog for connecting different parts of your design. Since Verilog is essentially used to describe hardware elements like flip-flops and combinational logic like NAND and NOR, it has to model the value system found in hardware. Verilog supports 4 values to model the functionality of the real hardware. A logic 0 would represent ground and hence a value of volt. A logic 1 would represent the voltage supply watt, which can range anywhere between 0.8 volt to more than 3 volt based on the fabrication technology node. Capital X or small x means that the value is simply unknown at the time and could be either 0 or 1. This is quite different from the way x is treated in Boolean logic, where it means don't care. As with any incomplete electric circuit, the wire that is not connected to anything will have a high impedance at that node and is represented by Z. In addition to logic values, strength levels are often used to resolve conflicts between drivers of different strengths in digital circuits. Value levels 0 and 1 can have the strength levels listed. If two signals of unequal strengths are driven on a wire, the stronger signal prevails. For example, if two signals of strength strong 1 and weak 0 contend, the result is resolved as a strong 1. If two signals of strength weak 0 and weak 1 conflict, the result is an X. Because two drivers of a net have the same strength but different values, then signal value will be unknown. Nets are used to connect between hardware entities like logic gates and hence do not store any value. The net variables represent the physical connection between structural entities such as logic gates. These variables do not store values except trireg. These variables have the value of their drivers, which changes continuously by the driving circuit. Some net data types are wire, tri, WR, tri-or, WN, tri-N, tri-0, tri-1, supply 0, supply 1, and trireg. Value of net data type is Z, that is high impedance, except trireg, which defaults to X. A wire represents a physical wire in a circuit and is used to connect gates or modules. The value of a wire can be read but not assigned to in a function or block. A wire does not store its value but must be driven by a continuous assignment statement or by connecting it to the output of a gate or module. Firstly, it's important to understand that the keywords wire and tri have identical syntax and function. However, they serve different purposes. The keyword wire is used for nets with single drivers, while tri is used for nets that have multiple drivers. In practice, multiplexers often use the tie declaration, and I'll show you an example of this. Here we have a simple multiplexer module named MUX. This module has 3 inputs A, B, and control and 1 output out. The out is declared as a tie net, indicating it can be driven by multiple sources, while the inputs are declared as wire. The module uses two conditional buffers, buffif0 and buffif1. Buffif0 drives the output out with the value of up when control is 0, otherwise out is high impedance represented as Z. Conversely, buffif1 drives the output out with the value of P when control is 1, otherwise out is Z. The key point here is that the net out is driven by B1 and B2 in a complementary manner. When B1 drives A, B2 is tri-stated, meaning it does not drive the net, and vice versa. This complementary driving ensures that there is no logic contention on the net. However, if there is contention, it is resolved using strength levels. For example, if two signals of opposite values but the same strength drive the net, the resulting value of the trinet will be x, indicating an unknown state. In summary, the try keyword is essential for scenarios where multiple drivers need to control a single net, such as in multiplexers. It helps to clearly indicate the design intention and ensures proper contention resolution. The keyword trireg is used to model nets that have capacitance and can store values. The default strength for trireg nets is medium. Nets of type trireg can be in one of two states. First, we have the driven state. In this state, at least one driver is driving a 0, 1 or x value on the net. The value is continuously stored in the trireg net and takes the strength of the driver. Second, we have the capacitive state. In this state, all drivers on the net have a high impedance represented by Z. The net holds the last driven value, and the strength can be small, medium, or large, with the default being medium. Let's look at an example of a trireg implementation. In this example, we have a trireg net named out with a large strength. We also have a wire named A and a control signal. The buff if one statement drives the out net with the value of A when control is 1. When control is 0, instead of going to high impedance, the out net retains the last value of A thanks to the capacitance modeled by trireg. This example demonstrates how trireg helps to maintain the last driven value when no active drivers are present, providing a stable output even in the absence of a driving signal. Let's start with try0 and try1. The keywords try0 and try1 are used to model resistive pull-down and pull-up devices respectively. A try0 net has a value of 0 if nothing is driving the net, with a default strength of pull 1. Conversely, a try1 net has a value of 1 if nothing is driving the net, also with a default strength of pull 1. Here is an example of a try0 implementation. In this example, we have a try0 net named out and a wire named out and control signal. The buff if one statement drives the out net with the value of a when control is 1. When control is 0, instead of going to high impedance Z, the out net gets the value 0 because it is declared as try0. If it were declared as try1, the default value would be 1 instead of 0. Next, we have the supply 0 and supply 1 keywords. The supply 1 keyword is used to model a power supply, typically connected to VCC. The supply 0 keyword is used to model ground, typically connected to GND. Nets declared as supply 1 or supply 0 have constant logic values and the strongest strength level supply. Here is an example of supply 0 and supply 1 implementation. We declare supply 1 for VCC, indicating that all nets connected to VCC are connected to the power supply. Similarly, we declare supply 0 for GND, indicating that all nets connected to GND are connected to ground. So, when we are designing digital circuits in Verilog, sometimes we face a situation called logic contention. This happens when multiple drivers try to drive the same net simultaneously. If we use a trinet in this case, we get an X, which stands for an unknown value, and that's usually a sign that something's gone wrong in our design. To handle this, Verilog gives us some special nets W or W and tri or trian. Let's break these down. W and stands for wired AND. This net performs the AND operation across all the drivers. So if any of the drivers is 0, the net value will be 0. Think of it like a chain. If one link breaks, the whole chain fails. W or stands for wired OR. This net performs the OR operation. If any driver is 1, the net value will be 1. It's like having multiple switches to turn on a light. If any switch is on, the light is on. Try OR and triand work the same way as W OR and W and W and, but are used in slightly different contexts, often involving tri-state logic. First we set out 1 to using buff. Then we try to set out 1 to 1 with buff. Because out 1 is a W and net, it performs an AND operation. Since we already have a 0, the final value stays 1-B0. First we set out 2 to 0, then we set out 2 to 1. Because out 2 is a W or net, it performs an OR operation. Since we now have a 1, the final value becomes 1BA. So the final values are for out 1 1-B0, for out 2 1-B1. Thank you for watching. If you have any questions, just leave a comment below. Have a great day.